Hello, everybody. I'm Pratusha Das, a PhD student at University of Southern California. And today I'll be presenting my research topic on human motion data analysis using graph-based techniques. Human motion analysis has many applications, for example, in gaming, human-robot interaction, rehabilitation, and sports, etc. But how can we do human motion analysis? We can do from videos, but are there any other alternatives? So we can also use motion capture data. That means the position data of human skeleton body or human hands. And the advantage of using motion capture data over video is that it reduces the complexity, it reduces the space, and it also preserves the privacy of the scene. Now, how can we extract motion capture data? We can use devices like Kinect, which gives us 3D key points of body joints, hand, and facial landmark, or we can use OpenPose software, which can extract these position data only using videos. Now, in this research, our goal was given position data of your hand key points, if we can understand or design a model to understand hand activity. So in my first chapter, my goal is to answer these questions where I'm trying to understand complex actions in an unsupervised way. I'm trying to find better representation of this hand motions. For example, we can use graphs. And the third one is, are these representations interpretable? So given this position data of hand key points from this OpenPose or devices like Kinect, which basically gives you 21 2D, 3D coordinates of each hand, we can design graphs like this one. This is our first proposed hand graph. This is human hand anatomy inspired, and it has also 21 nodes, and it is fixed and undirected. The second graph, I'm proposing a left-right hand graph. So to do any task, we use both of our hand. And that's why we are proposing this second hand graph, which is a left-right hand graph. And here, this can capture the relative motion between the two hands. It has 42 nodes, and it is also fixed and undirected. And to design this graph, I'm joining the tip of all the fingers in your left hand to the tip of all the fingers to your right hand and the base of the hands as well. Now, I'll just give you a little preliminaries on defining graphs. So we define graph using adjacency matrix, which incorporates all the information about that graph. We define the degree of any node I as the sum of the weights of the incident edges. And then we define the Laplacian matrix, which is the difference between the degree matrix and the adjacency matrix. And we use the eigenvalue decomposition of this Laplacian matrix to define our graph Fourier basis. So we define the graph signal on the vertices of the graph. For example, in this graph, I'm defining the graph signal on V1, V2, V3, and so on. And if you consider our application, which is the hand graph, we define the graph signal on each of these nodes. And in our case, the graph signal is the position of let's say, the tip of the finger or the motion vector, how the tip of the finger is moving from one frame to the other. That is the graph signal in our case. Now, how do we do graph Fourier transform? We do an eigenvalue decomposition of this Laplacian matrix, and the eigenvectors represents your graph Fourier basis. And then we take an inner product between this graph Fourier basis and our signal X, and the graph Fourier coefficients represents the feature extracted from the data. The benefits of using these graphs are the representations are interpretable. We'll see the examples later. And this feature extraction technique is also unsupervised. The processing can be done in real time. This is very fast. And the feature extraction is also application agnostic. So as I mentioned that the graph Fourier transform bases are interpretable. What do I mean by that? Here in the first figure, I'm plotting the first graph Fourier basis, which is corresponding to a graph frequency lambda equals to 0. And I have represented the values by colors. So green means the positive, red means negative, and blue means 0. And as you can see, this first graph Fourier basis corresponds to lambda equals to 0, captures the average of the signal. And the second on the right one basically captures a variation of your thumb to the rest of the fingers. Now let's see the interpretation of the frequency of left-right hand graph. Now in this case, this graph Fourier basis corresponds to lambda equals to 0, captures the average of the signal. This one captures the variation of the signal in the thumb to the rest of the fingers. This one corresponds to lambda equals to 0.26, captures the variation of from your left hand to your right hand. And this one captures the variation in your top of the hand to the base of the hand. Now, so far we have seen the spatial hand graph, and we can use some temporal model like temporal pooling, mean pooling to model the temporal part of the data. But can we design any spatio-temporal hand graph to capture the spatial correlation of the data and the temporal correlation together? And to do that, we define the spatio-temporal hand graph, which is nothing but the Kronecker product between the spatial hand graph and the line graph. Here, line graph is basically the line graph has cardinality or the number of nodes is equals to how many frames are there in the window. So let's say one window has 30 frames, then the cardinality of the line graph is 30. And once we do this Kronecker product, this is the spatio-temporal hand graph. And the basis, the Fourier basis is also the Kronecker product between the skeleton graph basis and the line graph basis. Now, as this hand graph has some interesting properties like this is tree structure. So this spatio-temporal transformation is a separable transformation. That means we can first apply the spatial graph transform, and then we can do the temporal graph transform. And here, as you can see, like once we capture the or extract the graph Fourier basis, this is the inner product between the graph Fourier basis and the graph signal, and alpha represents the features. Now, as I mentioned that this is the application agnostic technique, so I'll show you application in two different applications. The first one is in an unsupervised segmentation task. In this case, we divide the data into small temporal windows and then extract features using this spatio-temporal graph Fourier transform. And then we use segmentation model. In this case, I'm using a clustering based approach to do the segmentation to find the segmentation instances. So in this case, our task is given a hand actions, a series of hand actions. For example, if you are working in the kitchen, you're chopping vegetables, then you're throwing everything in the pan, then I want to find this segmentation instances when I'm moving from one action to the other. And if you look at the performance of this method, so first, the features I'm using is directly the motion vector. Secondly, I'm using the spatial graph transform to extract the feature. And then I'm using a separate temporal pooling model to extract the temporal pattern. And at the end, I'm using a spatio-temporal graph transform to extract the features. And you can see that the spatio-temporal graph Fourier transform features are performing the best. Now, we can also apply the same feature extraction technique in a recognition task. As I mentioned, this is a completely unsupervised feature extraction technique. But for a recognition task, we need to do some learning of the model in the which is there in the action recognition model. So first we extract the features in an unsupervised way, and then we design a classification model. Here in this case, we are using SVM to do the job. And we are using different train test ratio while training the SVM. So the first one is I'm changing the train test data set. And the second one is cross-person setting, where I'm training the system with 5 persons and testing it on the 6th person. That means the model did not see any data from the 6th person, which is a more real life scenario. I'm using FPHA dataset, which has 45 action and interacting with 26 objects. But the interesting part is we do not have any background information. We are just using the skeleton position information. So if I am drinking milk or drinking water, I do not have the information about the bottle or the glass of the water. And in this case also, our baseline method is LSTM, a long short-term memory. And I'm comparing the features extracted using a spatial graph with the temporal pooling, and also the spatio-temporal graph features. And you can see that the spatio-temporal graph features are always performing better. So to conclude this first chapter, I have designed a spatial and a spatio-temporal hand graph to extract the representation. This method is application agnostic and unsupervised. And to show that this is application agnostic, I have shown application in 2 different scenarios like segmentation and recognition. Now I'll move on to my second chapter, where the question is, so far we are not learning the representation from the data. Now the question is, can we learn the representation from the data, and what choices we can make to reduce the complexity? So in this case, inspired by the success of neural network, we wanted to design a graph-based neural network model to do this action understanding task. As graph, we want to do graph-based because it can capture the spatial correlation of the hand. And this hand graph, what you have already seen, has many interesting properties. That is, it is symmetric, bipartite in nature, and it is also tree structured. Now, I'll just give you a little preliminaries on graph convolutional neural network. So given this neural network, where you have seen the multiple layers of graph convolution, what actually happens is when we apply this graph convolution, it basically take a weighted average of all the neighboring node and itself. And this is this kind of filter we are applying or using in many number of different graph filters. We are using in a single layers, and we are using multiple layers of this graph convolutional filter to construct the graph convolutional network. Now, inspired by the work of Yan et al., where they defined the spatio-temporal graph neural network for full body skeleton data, we extended the work to the hand skeleton data. So we have already designed this hand graph and the spatio-temporal hand graph. And then we can extract, after each layer of graph convolution, we extract the features using this equation, where A is the normalized adjacency matrix, Q is the age weight matrix, Xn is the input data, and W is the stacked weight vector. So basically we are learning this W from the data. And in the network, first we have this input transform stage, and then we have different layers of spatio-temporal neural network, and then we get the labels. Now, given this symmetric and bipartite graph, hand graph, we can decompose it to smaller subgraphs. So Lu and Ortega propose that if a graph has interesting properties like it is bipartite in nature or tree structured, we can decompose it to smaller subgraph with an equivalent Laplacian matrix. And handling this smaller subgraph, computation with this smaller subgraph will be less complex and more efficient. And we are exploiting that idea to design better representation or extract better representation from the data in our hand activity recognition. Now I'll just give you a little preliminaries on graph decomposition based on symmetry. So this is an example graph where you can see this graph is symmetric around this green nodes, and we can decompose it exploiting this symmetry to the smaller subgraph, which is this left one. This is the symmetric part. This basically captures the symmetric part of the data, and this G2 minus basically captures the anti-symmetric part of the data. Now, given our hand graph, which is symmetric around this green finger, we can decompose it to smaller subgraph. Here, this is the symmetric part, yellow one is the symmetric part of the data, and this is the anti-symmetric part of the data. And again, this GH plus, you can see this is again symmetric around this middle finger, and the further decomposition is possible. And this is the final decomposed smaller subgraph. And they have equivalent GFTs. Now, the equivalence of their GFT or the Laplacian matrix is related using this equation, and computation with this Laplacian matrix is also less complex. So number of summation and multiplication, if you use this L5, will be much lesser. But as they are related by this matrix B, so if you are going to use this L5s, which is the decomposed subgraph, you need to pre-process your data first, and that will be used as input while dealing with this smaller subgraph. And this B is a hard unit-based orthogonal matrix. And we will see this pre-processing technique is basically interpretable. So this is a pre-processing block. And at the end, you get these values. So X was your input, these are the output after pre-processing. And I have grouped them to this phi 1, phi 2, phi 3, phi 4, because this phi 1, phi 2, phi 3, phi 4 are the input to this G1, G2, G3, and G4. Now, if you look closely what this phi 1 captures, this basically captures the symmetric part of the data. Phi 2, phi 3, phi 4 basically captures the anti-symmetric part of the data. So this is average of the signal. This is the difference of the signals. Now, let's consider an example where you are going to grab one object. The variation of your finger, motion of the fingers are changing. So the anti-symmetric part is more important. But when you are taking an object from one place to the other, you have a constant signal, or all the joints have a constant velocity. So the symmetric part of the data is more important. So if we use separate temporal kernel for each of the symmetric and anti-symmetric parts, then we will be able to capture much useful information. And we are using that idea to design the symmetric subgraph spatio-temporal graph neural network. So we decompose it, use separate temporal kernel, and at the end we concatenate all of the features. And basically the network is the same. So this is the final network. We have this input signal, we have this input graph, we decompose it into smaller subgraph, use separate temporal kernel for each of them. Then we do data normalization, we pre-process the data, and then we apply different layers of S2SDGCN. At the end, we do feature concatenation and use global pooling and softmax to get the labels. So we are, in this case also, to analyze performance, I'm using the same FPHA dataset. And here this SDGCN 3733 means how many number of layers of SDGCN I'm using. And just to compare, so now we are decomposing the hand graph based on its symmetry. But instead of that, if we just use separate graph for each of the finger, what will happen? And there's no pre-processing involved. And that is this FSTGCN, that is finger connected STGCN. And we have seen that S2 STGCN can achieve the best performance even with much lesser number of layers. So to conclude my work, we have designed a hand graph decomposition based on symmetry of the hand. I have used separate temporal kernel to model each of the smaller subgraphs, and S2 SDGCN can achieve better accuracy in complex hand activity recognition. And this method is generic and can be used for any graph structure with similar properties like symmetricity and bipartiteness. And these are the related publications. Thank you so much for your time, and please email me if you have any questions. Thank you.